Okay, in this video I'm going to talk about what's called Descartes' Rule of Signs. And usually you see this in an algebra class, and what it has to do with, it just tells you one of the big questions, in general is if you have an equation and you set it equal to 0, what are the solutions? And that's a hard question to answer in general. So Descartes' rule of signs says for a specific case, if you have a polynomial, it's not going to actually find the roots or the zeros of that polynomial, but it'll give us some information about what could happen. So not a direct solution, but at least you're getting some information, I guess. So it says, let p of x be a polynomial with real coefficients and a non-zero constant term. This is going to be important, having a non-zero constant term. We'll revisit that in one of the problems. It says the number of positive real roots is either one of the two following. It says it's either the same as the number of variations of sign in the polynomial, or it's less than the number of variations of sign of the polynomial by a positive even integer. So we'll definitely talk about what all this means. To get the number of negative real roots of the original polynomial p of x, we are getting information about the original one, p of x, but we actually have to look at a slightly different, a modified version of that polynomial. And what we do is, everywhere there's an x, we plug in negative x. And it says the number of negative real roots of p of x, that original, it says it's going to be very analogous. It's going to be the number of variations of sign in this new polynomial, p of negative x, or it says it's going to be less than the number of variations of sign in p of negative x by a positive even integer. Whew. Okay, it sounds worse than it is. So suppose, so we'll talk about, actually calculating these polynomials and counting the variations, the number of variations, but just to start off with, suppose we have our polynomial p of x and we count and we conclude that it changes sign 6 times. What that means is, it says, well, there can either be 6 real roots. It says, again, it can be the same as the number of variations, so you can either have 6 roots, or now you just have to start dropping, you have to start decreasing by multiples of 2, basically. So it says that there can either be 6 real roots, or 4 real roots, or 2 real roots, or, hey, 0 real roots. I should even say real positive roots, because that's what the p of x deals with. Okay, so there can either be 6, 4, 2, or 0 real positive roots. Suppose we look at p of negative x. So we would have to actually calculate p of negative x. You'll have to do a little bit of simplifying on that. Suppose p of negative x for some reason changes sign, I don't know, let's say 5 times. It says then there can either be 5 negative real roots, or again, we just decrease by multiples of 2. There can either be 5 negative real roots, or 3, or 1 real roots. So let's actually do a couple of computations here. But again, all you're doing is just counting and then just using these results. So let me find the examples I want to do here. So example 1. Suppose our polynomial p of x is 2x to the 5th minus, how about 3x squared minus 3x plus 6. Okay, so I'm going to emphasize, I'm going to put a positive out front because it is positive 2. Notice this fits the format in that we've got a constant term hanging out, and again, a constant term just means there's no x, no variable attached to it. And we have real coefficients. So notice it goes from positive to negative, so that's one sign change. It goes from negative to negative, so it didn't change sign, so we still have a total of 1 sign change at this point. And then if we go from negative to positive, to me that's a total of 2 sign changes. So I just kind of count as I go from term to term. So there's 1 sign change, it doesn't, so we still have a total of 1, and then we have a total of 2 sign changes. So what that means is, it says the number of real positive roots again, it can either be 2 or it can be any, we have to subtract away multiples of 2. So we can either get 2 positive real roots in this case or 0 positive real roots. Okay, so if we want to look at the number of possible real negative roots, we have to examine p of negative x. Okay, so again, all that means is where there originally was an x, we just replace it with negative x. Have to be a little careful here with our order of operations just to make sure that we get the signs correct. Obviously, that's kind of the whole gist of these problems, so you have to be real careful with the signs. Well, remember, if we take a negative number and raise it to the 5th power, it stays negative. So when we simplify, we'll get negative 2x to the 5th for our first term. We have to square the negative x first, so negative x times negative x will be positive x squared, but then we have to distribute the negative 3, so it'll still stay negative 3x squared. It looks like we get positive 3x when we simplify the negative 3 and the negative x, and then we have our plus 6 hanging out. So we do the same thing. We count the number of sign changes, and I think this is kind of this part also illustrates something important. So we start with a negative, it goes to a negative, so to me we've got 0 sign changes so far. I go from a negative to a positive, hey, that's 1 sign change. From positive to a positive, well, that's still a total of 1 sign change is. So again, what the result says is, it says the number of negative real roots, so the number of negative real roots, it says it either has to equal the number of sign changes in p of negative x, okay, so it says there's either 1 or it says you decrease by multiples of 2. But if we decrease by a multiple of 2, well, we're going to get negative 1, and certainly you can't have negative 1 real roots. So really it says the only possible thing is for there to be 1 negative real root. There's no other possibilities. So in this case, we actually know that there is exactly 1 negative real root. The idea is, in the other case, you know, I think the numbers were 6, 4, 2, and 0. So either we've got 6 or 4 or 2 or 0. And in this case, the idea is, well, you either got 1 or, well, that's it. You got 1. Okay, so that's the only thing that can happen. Well, that means you do have 1 negative real root. Okay, let's maybe do one more example here real quick. Again, pretty tedious stuff, definitely not the most thrilling thing in the world, but just kind of a clever observation again. You know, finding roots again is very important. You know, maybe if we can't do it directly, at least maybe we can get some insight. Okay, so same thing, p of x equals 6x to the 6th minus 3x squared minus 5x. So again, we're interested in the number of real roots and the number of negative real roots. But notice this polynomial now doesn't fit the form because it says before you can use Descartes' rule of signs, it says you want a non-zero constant term, and we don't have a constant term here. I mean, we could write plus 0, but again, we need a non-zero one. So what we do to get started is we simply factor out an x. So we would then have 6 x to the 5th minus 3x to the 1st minus 5. And if we were to set this equal to 0 right now, we would set the first part equal to 0, so we know that x equals 0 is a root, okay, of this polynomial. But we also want to know what happens to this other part, you know, 6x to the 5th minus 3x minus 5. We want to know, you know, what happens to the roots of that factor, and the idea is we'll now just use Descartes' rule of sign on this 6x to the 5th minus 3x minus 5 part. So maybe I'll call it q of x, just to give it a different name. So we've got 6x to the 5th minus 3x minus 5. So again, if we count the number of sign changes, okay, it goes from positive to negative. so that's one sign change. And then it goes from negative to negative, so still that's only one sign change. So just like before, it says the number of positive real roots. It says the number of positive real roots. It says it's either 1 or, well, again, there's no other possibility. So it says the number of positive real roots is exactly, in this case, number of positive real roots is exactly 1. Okay, so far we know that 0 is a root of the original polynomial, and we also know that there's exactly one positive real root. Well, we have to do the same thing to count the number of possible negative real roots. Thrilling stuff, right? So we have to look at q of negative x. So we'll get 6 times negative x to the 5th minus 3 times negative x minus 5. Again, negative x to the 5th is going to be negative x to the 5th. So we'll get negative 6 to the 5th. Our middle term will turn into positive 3x, and then we'll have negative 5. If we count the number of sign changes now, it goes from negative to positive, that's one sign change. It goes from positive to negative, that's our second sign change. So it says the number of possible negative real roots. So it says the number of possible negative real roots. It says it's either got to be 2, or we can bump it down by a multiple of 2, which would give us the other possibility of 0. So in summary, for this original polynomial, we know x equals 0 is for sure a root. We know the number of possible negative real roots is either 2 or 0. And we know, in this case, we know that there's exactly one positive real root. So what does that tell us about the other roots? Well, it tells us there must be some complex roots. So if you've seen complex numbers, that's what's going on. So, alright, I hope this example makes some sense and helps you out. Again, pretty long, pretty tedious. I hope I didn't misspeak. Feel free to post comments and questions as always, and good luck out there.